If we put the previous two theorems together, and just to quickly repeat those results, what we've shown is that if we look at z mod m, so integers modulo m, then there is a well-defined addition operation that takes a congruence class, well, two congruence classes, and their sum is just you take a representative from each, say A and B, and you add the representatives and you see what congruence class that is. So as a quick example, suppose we were in, I don't know, z mod 9. We could take, for example, 3 bar plus 7 bar. So that's 3 plus 7 bar, which is 10 bar. Modulo 9, that's the same as 1 bar, though. And the claim is that, or the theorems prove that this is well defined, namely, if we were to represent 3 in a different way, say as maybe 12 modulo 9, we would get the same answer. So let's just quickly do that. Let's suppose we represented 3 as 12 instead. It's the same equivalence class. Then what would we get? We'd get 19 modulo 9. And the remainder, when you divide 19 by 9, is 1. So you get the same answer. That's what well-definedness means. And then we also have this operation of multiplication where you pretend that they're integers, you multiply, and then you reduce. Or you look at the corresponding equivalence class. So for example, let me use a different z mod something. Let's do maybe z mod 10. If I wanted to multiply 3 and 7 in z mod 10, that would be 21 mod 10, because we're supposed to just multiply the 3 and the 7, and 21 mod 10 reduces to 1. Great. And so the previous theorems prove that these operations make sense. We don't have any issues where we get more than one answer for the product of two congruence classes or the sum of two congruence classes. And so in particular, we have an addition and a multiplication structure on z mod m. And it's sometimes helpful when you have these to get a feel for the operation to write out addition and multiplication tables. So we're going to start with, we're going to do two examples here. We'll do a sort of a silly example. We're going to start out with z mod 2. And we're going to look at the addition table and multiplication table. And then after that, we'll do a little bit more serious of an example, maybe z mod 7. Or let's see, 7 is also a prime. Maybe z mod 4. We'll do z mod 4 after this. No, I'll decide what we're going to do after this when we get there. But we're going to do z mod 2 now. So how do we do this? Well, let me draw a table here. I'm going to say in the upper left that we're going to do plus. This is going to be our addition multiplication table. And what we're going to do is we're going to list the elements of z mod 2 as columns, and also the elements of z mod 2 as rows. And then when we have the row and the column intersecting, we do the corresponding operation. So 0 plus 0 in any reasonable world is still 0. Let me use blue or something. So this is a 0. 0 plus 1 is 1 mod 2, so that's a 1. 1 plus 0 is 1 mod 2, so that's a 1. 1 plus 1 is 2 mod 2, but 2 is 0 mod 2. So we think about the 0 as sort of the right answer. So that's our addition table. Now we're going to do our multiplication table. So again, I'm just going to put the operation in the upper left. I'm going to do times here, and then 0, and then 1, 0, and then 1. 0 times 0 is 0. 0 times 1 is 0. 1 times 0 is 0. 1 times 1 is 1. And 1 mod 2 is still 1. So if we wanted to know how to do arithmetic in z mod 2, these tables tell us how to do this. And on your homework, you're going to be asked to compute some addition and multiplication tables for various ZMod ends, and you're going to just do this. So let's do one more example. Let's see. Let's do, I think, ZMod 6. We're going to do the add multiply table. All right, so this is going to be a little bit more involved. Let's just go through it a little bit quicker though. So 0, 1, 2, 3, 4. We got to go all the way up to 5, and then 0, 1, 2, 3, 4, and then all the way up to 5. Okay, when we add 0 to any one of these, what are we going to get? Well, we're going to get whatever we're adding to because 0 is the additive identity, so we can just fill this in. Similarly, when we add 0 for the column, we can just write out what we're adding to our 0 because 0 is the identity. And let me also note here that addition is commutative, and that's something you're going to prove in your homework. That is, it doesn't matter the order in which you add things modulo m. It's the same thing, and this is roughly because it doesn't matter in Z. Why should it matter now? Now, what that tells you is if you're going to do a row plus a column, that's the same as doing that column plus that row. So it tells you that this table is symmetric about the diagonal. We already saw that in ZMod 2 actually, but it's symmetric. And what that means is we really have to just work out one of the triangles, one of the upper or lower triangles in this picture. And once we have that, then we just reflect. So let's do the diagonal next. Let's do the diagonal next. So 1 plus 1 is 2. 2 plus 2 is 4. 3 plus 3 is 6, but mod 6, that's 0. 4 plus 4 is 8, but 8 mod 6 is 2. 5 plus 5 is 10, but 10 mod 6 is 4. Great. 1 plus 2 is 3. 1 plus 3 is 4. 1 plus 4 is 5. 1 plus 5 is 6. But 6 is 0, mod 6. 2 plus 3 is 5. We're seeing a pattern here now, right? So you just increment by 1. 2 plus 4 is 6. 6 mod 0 is 1. 2 plus 5 is 7. 6 mod 0 mod 6 mod 6 is 0. 2 plus 5 is 7. 7 mod 6 is 1. And then we can just sort of fill in these. And then since it's symmetric, we're just going to flop. So this row is going to be the same as this column. So 3, 4, 5, 0. And then this row is going to be the same as this column. 5, 0, 1. And then same as this column. So 1, 2, and then 3. That's a little bit too big. All right, so if we wanted to do addition in ZMod 6, we have this table that we can resort to. And that's the end of the addition table. Let's work on the multiplication table now. And let me observe the same thing that we observed with the previous problem. Multiplication is also commutative. So this also tells us the table is going to be symmetric. So we, again, only have to do half of it. Well, we only get to do half of it. And then the other part is almost the same. You just reflect. So 0 is the, as I say in class, this is the void. What do I say? I say a couple things. This is the great annihilator, or the void. And so when we multiply through by our 0, it's just going to 0 everything out. One is the multiplicative identity. That is, if I multiply by 1, nothing happens. So when we multiply through by 1, nothing happens. Multiply through by 1, nothing happens. Now all of the interesting things happen when we're not multiplying by 0 and 1. So 2 times 2 mod 6 is 4. 2 times 3 mod 6 is 6, but 6 is 0 mod 6. 2 times 4 is 8 mod 6. 8 mod 6 is 2. 2 times 5 is 10 mod 6. 10 mod 6 is 4. I'm going to start in this spot. 3 times 3 is 9. 9 mod 6 is 3. 3 times 4 is 12. 12 mod 6 is 0. Did I do that right? Yeah. 3 times 5 is 15. 15 mod 6 I think is also 3. Then we're going to go here. 4 times 4 is 16. 16 mod 6 I think is 4. 4 times 5 is 20. 20 mod 6 is, let's see, 18, so it's 2. And then lastly, 5 times 5 is 25, but 25 is 1 away from 24. So, and then all we do is we reflect. So 4024 is going to be 4024. 303 is 03. 421. So now, if you don't like the reflecting business, that's fine. You can sit there and multiply them, and that you'll get the same answer. You have to get the same answer because multiplication is commutative. But anyways, when you do these for at least for the integers, mod m, it's a symmetric table that we're going to get. And so this is the multiplication, and then we just did the addition table. So now we know how to do arithmetic. Arithmetic is the math of adding and multiplying. Modulo 6.